Okay, so to summarize the questions, it was about assignment 2, and the question is whether it's possible to give more unit tests for each of the components. And that's definitely a good oversight. And if you see that we have a small unit test for the blue test scores, right? Which is basically, which is not the conclusive test, but it gives you a generic idea that if your method is working. Yeah, so I mean, some of the questions is hard to give you the unit test without giving away the answer, or maybe it would be like a part of the assignment for you to design your own unit tests and sort of test out, like this could be a good exercise for you to use those unit testing. But it's definitely a good idea that we plan to add to coming years maybe, but this was the first time we're introducing this assignment, so we didn't get a chance to do that, but I definitely agree that having that unit test and having basically what we did before was that we had a whole bunch of tests for marking, and we'd just expose or avail 1 or 2 easy tests to the students so that they can like check overall efficacy. But this year we don't have that, but it's, I mean, I'll see, like it depends on the TA hours and everything, logistics-wise, but otherwise, like I would ask you to do the kind of unit testing yourself. And another, seeing this in a positive light, like I think, you know, the bug that you had with the transpose of the matrix, right? So I think the time you spend, it will make it stick, and you'll never make that mistake again. So, you know, that's how you learn, right? So anyway, it's all in the learning process. Okay, so 2 quick announcements. Final exam date has been released, so you should already know this, April 25th from 2 p.m. to 3 p.m. And sort of, I don't have a lecture plan for today because my plan is to go as much as I can, and whatever we have covered we'll include in the exam. And some of the materials could be just simple reading materials like benchmark information. Those are not that I mean, you can do them yourself. And from next lecture, Wednesday, my colleague, like my co-instructor, Sean, will be taking over, and he'll be getting started on some, you know, ASR and all the school stuff, right? So we'll be ending LLMs discussion today. Okay, so we stopped at, so what have we seen so far? So we know how, like we have seen neural language models and how to train them. And we have seen the transitions from BART to T5 to GPT-3, and that's where I said that the LLMs sort of pivoted and took off, and we started seeing these emergent behaviors. We saw that emergent behaviors like in-context learning, where you change the prompt, sort of gives you a different answer. You can give few-shot versus zero-shot task completions, etc. And then let's refer to them as PLM. By PLM, P means pre-trained language models. And we also looked at how then the paradigm of taking this large pre-trained models and then fine-tuning them for downstream tasks, how to do that. And then today's conversation will be how we can align these language models to follow instructions to like human preferences. Now, example like what ChatGPT does, right? And in TLDR, the solution is that okay, so before we talk about that, why do we need to align? So we really need to understand that why do we need to align? Why can't we just use those pre-trained language models and why can't we achieve performance like ChatGPT? So we'll talk about this pipeline for instruction fine-tuning called reinforcement learning from human feedback, or RLHF. Note that there are other variants to it, but instead of covering everything in a little bit, we'll try to go deeper for one pipeline and understand how the mechanism works in depth, okay? So the first question is, why do we need alignment? And the intuitive idea is that the way we've been training language models have some intrinsic misalignments with human preferences. And it will make a lot more sense when I go through some examples that what I exactly mean by human preferences. Okay, so this is recall. From previous lecture, recall that what is our language modeling objective. So you're given a corpus and you train your language model based on the cross entropy of the corpus. So essentially, you're maximizing the probability of text tokens in that language model, right? You're minimizing the cross entropy loss. Now, my argument is that LM objective, language modeling objective like this, can be misaligned with the desired goal of high quality output generation. And my question to you is that, can you think of any reasons why that would be? So think of like what are we doing in language modeling? We're just we're maximizing the probability of the next token, right? Like given something, we're maximizing the probability of the next token. So if you're trained like that, a simple answer could be, when I say high quality output, you could get low quality output. Why would you get low quality output? Because you have trained on toxic data, you have trained on like unfiltered Reddit data, and there can be some examples there which are toxic, which are not true, which are made up, etc. Things like that, and you don't want that. That's low quality, right? So it's misaligned. But so similarly, so here's some limitations. Okay. So first is there's no granularity or distinction between important errors versus unimportant errors, okay? So for example, for an unimportant error, let's say I say that we all live in house, or we all live in a house, and the language model predicted we all live in a home, okay? That's one error. And the second error, I'm saying Toronto is a city in India versus Toronto is a city in Canada. So I urge you to think that the second mistake, I think you'll agree with me, is a little bit higher than the first mistake where the language model is generating, we all live in a house, or we all live in a home, right? So it's like a different synonym, but still, let's say as an example. So basically, with the language modeling objective, we're penalizing all errors equally. So that can be right? And the second point is, what I alluded to is that it will put a probability mass on anything it's fed on or it's trained on, right? Whatever is in the supervision data set. And in general, I would argue that anything to do with language generation is intrinsically subjective. So, and we talked about this in machine translation, right? So you can have the same translation, have the same meaning, but say it in a different way. So in order to judge which one is better, it's generally a tough problem to apply heuristic measures to qualify natural language because it's so intrinsically subjective. So because of these reasons, aligning the language model to actual human preferences, what a human would actually like, is a much better way to optimize the language model or have better quality, high quality output from our perception. Okay, and so this was, I mean, there's many works, but I think this work is sort of explicitly shows this, that you can take English summarization task, and it was in Europe's 2020. So Steen et al. So English summarization task in 2020 was already a NLP benchmark task, like summarization. The task is you give some task and you summarize, right? And what they showed was that you can use this kind of optimization using human feedback to obtain better results, right? So if you look at this data set over here, it's a TLDR summarization data set. The idea is that you have a ton of like posts from Reddit and subreddits across a variety of topics, which you're probably familiar with after A1. And then there's a human written reference. And then there's a supervised model. So it's a large language model that has been fine-tuned for the summarization task, okay? Using like, there's no, and then they did this human feedback model, which is basically like using the alignment that we're going to see using this RLHF or whatever alignment procedure. And the results, they found that human feedback aligned results, majority of the fraction of the time, they produced better results that were more aligned better with human preferences. So this is like a example using one specific task that was already standard, that this approach works. So yeah, you can read this specific. So basically the supervised model is summarizing going on a date with a girl I met a few days ago, going to the beach, et cetera, which does not include some important caveats of the data, like the person haven't been to a date in a long time, and it was with the same person, first ever date, and what should I bring, like what kind of help to ask for. So essentially, from a human perspective, this produced a better result. This is a hand-picked example, but you can see, I mean, in general, like that was the case. So I think this is a very important point, so I'll try to do this with like an actual example. So for example, this is an instruction task, okay? And I have shamelessly plugged my work in the below, but this is essentially from a data set that asks language model to group 16 words into groups of 4 connected words, okay? Now, the thing is that if there's a language model just trained on language modeling objective, as I said, that it's just trying to produce the next most likely token. So then I'll first show the output of llama to 7 billion. So it's a 7 billion parameter model, which hasn't been fine-tuned, instruction fine-tuned, or which hasn't been aligned. So you can see that, and obviously it produces a different result if you prompt it again, but it's basically gibberish. It's not very helpful. And then it's the same model, but with instruction fine-tuning, we get an answer like this, a response like this, where it doesn't matter whether the grouping is right or wrong. That's a different question. But the point here is that it's actually following the task. And that's because, with this model, it didn't group the following 16 words. It doesn't understand the notion of what grouping means, like the instruction. Whereas this model is probably trained on samples where there's some instructions like grouping means this task, like I have to group this, right? So you can see the obvious improvement. And and the demo is worth 1,000 slides. So I want to do this for a demo for 2 reasons. One is to show my point, and the second one is also this JEMA 7 billion chat is a very recent model that probably some of you already know that was released by Google very recently, and I wanted to show you that how it's all of you can just quickly go and this is an applied course. You can really try it out to whatever you're doing. And it may also excite you. Doing more research on LLMs. So let me quickly, okay. So what you can do is there's a lot of frameworks, and so usually you already know about transformers. There's LangChain. There's but the point is that it's very simple to use. I'm going to use this hosting service called Replicate, and the first one I want to show is. We have llama 7 billion chat. So what you can do is you can just load these models. And this is the DeepMind model that came out very recently. And here you have the same task. You formulate the prompt that you saw on the slide. And basically you prompt different models. And so usually you'd put in a role and the content is the prompt. I'll cover a little bit in the prompting strategies. And usually GPT-4 is considered the state of the art, and everyone just uses that as the reference. So it does that without any problem. Again, we don't care about the grouping correctness. It just gives some new, it can be correct, we don't care about that. And then basically you can do the same thing for different models, essentially. So here I'm prompting a 7 billion, the llama to 7 billion, and you can see that it just produces some garbage. This is the result that I got, and yeah. And with llama 7 billion chat, you just get the result. You do the same thing. I think you get the point. And then JEMA. So this example might not show it, but the latest, the JEMA 7 billion compared to IT means instruction. Oh, you're not. Yeah, so IT here means instruction fine-tuned. So essentially it will be prefixed with chat or instruction fine-tuned, etc. Things like suffixes like that. And even though it's the latest model and it has a distinct better performance in considering other examples than, let's say, older model of the same size. But when we switch to, so 7 billion instruction fine-tuned is doing fine. It's grouping them by animals and places, the reasons. So this is the response. But the thing is that even JEMA 7 billion without instruction fine-tune actually doesn't solve the task. So that, and it makes sense, right? So that drives you the point that, these are why do we need instruction fine-tuning, okay? Anyway, let me, okay. No. Okay, please don't hang. Sorry, my presentation hung, but luckily I have a backup, so I'll, okay. Okay. So 7 billion, if I get the time, I'll just go over some of the compute requirements, but training a 7 billion model is not really possible for most individuals and even larger models, even most institutions. So there's few individuals and corporations, big research institute that can do it. So beginning 2023, Facebook's Llama 1 models were released. What they did was they pre-trained it and then they released the weights. So you could just download the weights and then you can apply it to your model and you have a pre-trained model. And so basically, and then you can use it as a foundation model, to do your fine tune on your task or do whatever you want to do. Because at the end of the day, if you see that architecture-wise, it's something that you already know. It's basically, I think you can write up the Llama base architecture in like some hundreds of lines of Python code. That's it. But it's on the data that it's trained and the size and the training mechanism is the bottleneck for public access for anyone to access it. So if you have the pre-trained weights, you're essentially have that pre-trained you have that power of having a foundation model. Some scientists are kind of against this release of pre-trained weights to the public because, for example, I was at Jeffrey Hinton's talk and he was like, this is like handing over nuclear weapons to anyone to do anything. And I think in the ethics lecture, hopefully you'll learn about some of the potential dangers of, allowing this or disallowing it. Anyway, so yeah, some properties and the point here is that this 13 billion parameter model was outperforming GPT-3 that we have seen before on most benchmark tasks. And since then, we have seen this notion of using an online repository like Hugging Face to train. So you have your pre-trained model, and let's say you're in different fields. You want a songwriter or something. You do your stuff, and you upload that model onto Hugging Face, and people will download it and use it for their purposes. So it became very popular. So it's then we have seen an explosion. This is a snapshot from yesterday, and see that Google Gemma 7 billion. It's almost like App Store now, right? Okay. So now let's dig down on this RLHF pipeline, okay? So I think I've convinced you that we need to align and why we need to align LM using human preferences. But we can have, obviously, human in the loop for training, because it'd be infeasible. But then the solution is then, what if we can replace the human with a reward model that mimics the human? So what the human is doing is, what the human labeler is doing is basically saying that, okay, you have two samples, you have two completions. I like this one. This one is better, this one is bad, okay? So just a binary classification, okay? So if you give me a prompt, and the human is, a prompt, let's say X, and you have two labels, and the human labeler is looking at the two labels and saying that, okay, I like this one better than the other. That's it. But if that's the case, then we can train a reward model that does the exact same thing, because we all know how to train a neural network model that will do binary classification, right? And that's essentially the idea. Okay? Now, next is that, okay, so you have that reward model that mimics human. Then how do you use that reward model to update your model parameters? Okay, so these are the two problems that I want you to think about, and we'll look into how we can do this. And the solution is that we'll be using reinforcement learning policy gradient update methods like reinforce a PPO using the RLHF pipeline. Just to gauge, how many of you here already know about the reinforce algorithm and how it works? Okay, so reinforce, this is not the main focus of this course in general, but I think it's important for you to understand this, especially to learn this pipeline. Okay, so there's essentially 3 steps to it. The first step is we use a high-quality human demonstrations data set, and we do supervised fine-tuning, starting with a pre-trained large language model, okay? So what that would mean is that we collect expert demonstrations from humans, and then we fine-tune our language model. Now, in the fine-tuning stage, we're not doing anything great. All we're doing is that we're training it just like with the LM objective on some new data, okay? Nothing new. We're just exposing the language model to a whole bunch of new data. Now, second step is we train a reward model using human rank preferences data set. So this step is like we do preferences sampling, and we'll get into the details of this, but the second step is simply to train the reward model that we talked about that mimics human. And if we have that, using step 2, we optimize the model in step 1 using the reward model in step 2 using reinforcement learning, okay? So 3 simple steps. Okay. Now, in step 1, there's nothing to say. It's basically you have instructions data set. You have collected an instructions data set, and you're basically doing fine-tuning to your LM pre-trained policy, okay? That's clear to everyone, right? Okay. The second step is preference sampling and reward learning. We train the reward model mimicking human preferences. So we can do this by simply starting. We can initialize our reward model with our step 1 SFT as a baseline. And then we add a head on top of our output layer that just outputs a scalar value, which is our reward, okay? Everyone understands this? Take the base model and then just add a layer on top of it that outputs a reward. And now we're going to train it. And we assume, so actually these two go in hand. So we have this preferences data set, which is denoted by DRM, which basically gives us a binary classification, okay? So 2 completions, 2 answers, whatever you want to call it, denoted by Y. One is chosen and the other one is rejected. So one is better than the other. And we can use this preference data set that gives us these samples and prompts, and we can train our reward model denoted by R using this objective function. So if everyone's clear on how we get this loss function, then we can skip the next few slides, but otherwise I have to, let's dig down a little bit deeper. So here we're basically trying to maximize the expectation for, so R theta is our reward model parameterized by theta, and X is our prompt, and YW is the winner, YL is the loser, okay? So we're trying to maximize winning samples, okay? So the intuition is that out of the 2 samples, if it's the winner, then you update those parameters of our language models, okay? You take a gradient step. Oh, sorry, this is the reward modeling. So in the reward modeling phase, we're just updating theta. Any questions? We'll look into how the loss function is coming in the next slide. So, okay, so let's dig a little bit deeper. What we're doing in step 2. So you have the preference sampling, and so first we do preference sampling. So here, whatever this DRM data set is, we assume that there's how do we do this? We prompt the model to generate samples. Okay, so we have a prompt X, and we ask our language model to generate 2 completions. And then we have a human labeler labeling which one is better. So if we have a tuple, consider that we have a data set, we've compiled a data set of these preferences, okay? That's our DRM. Yeah, so this is how, these are the pairs of FST. And we denote a winner between given a prompt X. And the assumption here is that, there's underlying latent human reward model, R star, for the best answer, the completion given X, okay? And our goal here is to learn a reward model that is as close to this as possible, okay? That's the assumption. So in order to model this, we need to model human preferences. How do we model it? There's few works on this, but I think the simplest and the one that is usually used here with the binary sort of pair comparison is the Bradley-Terry model that stipulates or models human preferences given two preferences y1 or y2, so here yl and y winner given x in using this, this equation, okay? So you can see that it's sort of like a normalized probability distribution, okay? And so if we have a model for human preference distribution, then you can use this, assuming that, you know, our samples are human, you know, comes from a human latent preferences reward model. We can parameterize our reward model using r theta xy and estimate the parameters using maximum likelihood by framing the problem as a simple binary classification with negative log likelihood loss. Does everyone agree with me? So this is simply like, you know, binary classification loss, and we know how to train a neural network model for this. This is easy. So r theta is a scalar like output for our enhanced or modified Bayes reward model, and for our prompt x, and yi is the completion, and sigma is the logistic function. Okay, so if everyone agrees with me, then this is how we can train. We have a reward model now, and usually in practice, to ensure that the reward function has lower variance, we'll normalize the rewards to have mean 0. Yeah.
So we take the difference because we want to maximize the gap between two of them responses.
Yeah, that's the idea, right? So you have a pair and you're trying to update your, like you have a reward model. Well, actually in the reward modeling phase, what you're trying to do is you're just trying to mimic human preferences. Like given, you're trying to mimic, if you're given a prompt and a sample, how would a human rate it, like the reward it, right? So you're trying to mimic that. And we'll sort of use this in step 3 to update our Bayes language model, which is now we're in step 3. So in step 3, we're going to do our, yeah. Oh, this one? So you can, I think the easiest way to think about it is like the exponential. So you know the softmax function, right? So you are given some probabilities and then you're sort of normalizing it, right? So if R star is your human preference, the latent oracle preference. It could be, no, it's just like you're normalizing it, yeah. So I think it can be conjugated. Yeah. Sorry, a star? Oh, no, star is just showing that it's the oracle. That's it, it's the best. It's the best reward. It's the best possible, it's the most, it's the closest reward model to a human preference. So our star here is just saying that it's an oracle reward model. Okay, that's it. It's just, yeah. And P star is the, oracle probability distribution. So.
How do we go, like I'm lost with, I don't see the P.
Okay, so all we're saying is that, okay, so in order to design an objective function, we need to model the preferences, right? So all we talked about is how do we model this? So we use the Bradley-Terry model, and note that what if you can ask that, what if there are more rankings? What if there are 3 choices, 4 choices, and things like that? So Bradley-Terry model is essentially a subset of what we call Plankett-Luce models in the case where there's only 2 options. But anyway, that's besides the point. The point is that we are just using this to model human preferences, okay? All it's saying is that human preferences can be modeled as a probability distribution P star, given 2 choices, one better than the other, given some X. This is how we can model this. So this is just a probability distribution, okay? And so once you have that probability distribution, then you can parameterize a reward model R theta X Y, and then you can basically update the parameters of theta based on this objective function. So you have like basically like, so this is a logistic function, and you have this winner, like the better answer, minus the worse answer. And then how would you do like a binary, you just train a neural network model for binary classification loss, right? So yeah, so essentially, yeah, so what it's doing, what's it gonna, if you train this with this, what is it doing? So it's sort of rewarding the model when it's answering, when it's picking the right answer as the human, and picking the right classification, right? That's what it is. So you have a human classification. So it's becoming more and more as you train it, this is becoming like a human reward model because it's classifying just like a human would, okay? Okay, so then the third step is RL optimization, right? So in this step, we're going to use, so far we have the base pre-trained supervised fine-tuned model, like our pi SFT from step 1, and we have the reward model trained as R. So we want to train for this optimization, okay? So it's basically saying that y is a completion given a prompt x. We want to maximize the reward, okay? And so how can we do this? So this is where the next few slides we explore this question. So then we know our objective function. How do we implement this? So one simple way you can say is that you can do like just train a neural network, do stochastic gradient descent. But this r theta is not differentiable. So we can just apply SGD with respect to like we're trying to update our model parameters phi. And usual SGD setting, what you do is like, you know, SGD, you just update taking the gradient towards the increasing objective. You just take a step towards that. But all of a sudden, we can solve this part using SGD. So we need to resort to some kind of other mechanisms like reinforce to estimate and optimize this objective, okay? And then after that, what we want to show that we can, after this, we want to be able to do this update and using this objective, but using, let's say, reinforce on PPO. Basically, we know this, we can update this. Now, what we want to see is that how would it work if you use reinforce, okay? So then we'll take a sort of detour into explaining how reinforce works, and then we'll come back to this equation. So remember this equation. So this is our objective. We have a reward model, we have a SFT base model, and we're trying to update the model parameters phi using this objective. We don't know how to do, we can do SGD, but we'll come back to it, okay? So slight detour. So how can we use this reinforcer? By the way, I think, in my opinion, reinforced algorithm is like the backbone of like, you know, the entire like whatever newer or fancier reinforcement algorithm that you see, bells and whistles. But at the very crux of it is this. So we need to take a gradient of, we want to be able to take a gradient of our objective, okay? Now, this is expectation, definition of expectation. And this our derivative is outside the summation block. What we want to do is, so we can do this. So this is just a definition of expectation, and by linearity of gradient, you can push the gradient parameter inside. And then what we can reformulate this using what we call the log derivative trick, which you may already know. But the idea is that if you take the log of something, log x, it's 1 over this probability distribution y, and then the derivative of p of y, okay? Everyone clear on this? It's just the, you know, applying chain rule to the derivative of log x, okay? And then you can rewrite it as, so you can rewrite this guy like this, just shifting the parameters. And then you can plug this back into the first equation. And what that gives us is something like this. And you can rewrite this yellow block as expectation, just the definition of expectation. And then you're left with, this is what we want. We can actually, once we have this in this form, this actually allows us to do sampling, do Monte Carlo like approximations, okay? So let's focus on this block over here. So we want to do expectation of this. We want to sample y hat, which are completions, okay? So let's say you have a completion, and you have the corresponding reward for this, okay? We have a reward model, let's say. You have the corresponding, and then you're trying to update the parameters based on this, right? So So what you can do is like you have a completion, you see the reward. If the reward is good, then you update the parameters likewise. If the reward is bad, then you can suppress the parameters. So essentially, you take a step towards it if it's a good sample. You take a step away from it if it's a bad sample. Okay. So now what we can do is that we can keep sampling like this, right? So you know that by Monte Carlo approximation. So you take you take 100 samples and then you divide it by 100, you get an average expectation score, okay? So that's what we're going to do. So we can approximate this objective using Monte Carlo sampling. And then we can sort of do an approximation by, you do n samples and then you divide it by n and then you have like a approximate value, right? So now we can go back to our objective here, which says that, remember that slide from the equation where I said that this part is, the blue part is that we couldn't do using SGD, but now we can do an update by replacing it with reinforce method, okay? Now we can update the parameters in this way. And the intuition is, what I said is that if the reward is positive, then update weight parameters phi to maximize this probability. Parameterized by phi. If Ri is negative, then update the weights to minimize this probability, okay? Now, this two slides, using reinforce is basically to show you that we can actually update. Our main goal was what? Our main goal is to update phi, okay? The model parameters phi, and we can use like reinforce to update the parameters if we have a reward model. Now we can go back to our step 3 with RL optimization. So our main goal was to update parameters phi of our language model PySFT from step 1 with the objective. So this is the objective. Where so this is sort of like the PPO objective, which is also like using an RL algorithm. So here we're sampling X and completions from our model, and then we're getting a reward using step 2 reward model. And then we're putting like this part on the right-hand side is just a regularizer that is controlled by this parameter beta. And what it's saying is that this DKL is the kill divergence of our trained model with some reference model. Usually this reference model is just our PySFT from step 1. So the goal of this part is to say that, do explore, but don't get too far away from our base model. So this sort of allows like, mode collapsing or, deviating too far away from our base training, okay? So this is just a regularizer. But if you look at the left-hand side, we're just trying to optimize this objective. And and then now that we have shown that we can do this using RL, we're gonna formulate this as a reward function. We'll formulate this objective as a reward function, and then we will solve it using any RL algorithm, which is typically partial proximal policy optimization. Any questions? Yeah. So each time, so I guess you're now training or you're updating the language model, right? So each time, so you're basically saying that for the same prompt, there'll be different answers, right? But we're only using, like, think of it as one training sample with X and, like the completion, right? So we're using a different XY pair. So we're using XY pairs, right? And also, so we're basically using a pair of like an X and Y with, so we're not using multiple, we're not using that X again. So I'm not sure what you mean. Like in a training process, I'm not really sure how your scenario would work. But maybe I'm not getting something, but we can talk offline. I just want, you.
And the only reason we're relying on RL right now is because the text returns a discrete and non-continuous
In this case, yes. Yeah. Well, do you know about the direct preference optimization or DPU? Or anyway, the point is, like, for our conversation, yes, but there are other techniques, newer techniques that skips or RL-free techniques to do it, and it's getting more and more. So you get analytical best solution, and then you use SGD or yeah. Okay, so now this is sort of the main paradigm, RLHF, and then after that, as you can imagine, this feedback can be from any source, and there's been an explosion of RLAIF, RL like reinforcement learning from AI feedback, from market feedback, from I don't know, animal feedback, who knows. But the point is, like, once we have that, so this is one such emblematic example, reinforcement learning from AI feedback. So here, the only difference is that if you take out the human, instead of the human preferences, you can basically model it like from any off-the-shelf LLM, right? You can train a reward model, right? So this preference data set is using pairs of completions, sorry, so it's the judgment of another AI model, okay? And the rest of the pipeline can be the same. Okay, so does this make sense? Okay. Okay, so let's switch our focus to prompting a little bit. And so now that we have like a trained model, so the prompting is essentially, so the point is that how you ask something or how you give the input to this trained language model now we have matters. And there's a lot of different techniques that, supposedly like has better way to prompt a language model. And it's a little bit of, it's a little bit of art because of two reasons. Because I think the whole prompting paradigm, the underlying models are also improving and changing, right? So basically saying that, if we do this way, for example, if we decompose a prompt using exactly this way, we'll give you better answers. We can definitely say that because maybe we're constantly generating data and their newer models are training on that data, and maybe there's some shift, but essentially what we're going to talk about, like the point is, high-level point is, the prompt design can be used to extract better utility from these pre-trained language models. And we have seen those glimpses with the GPT-3 slide, or the phenomenon of in-context learning, right? So you can ask something with no previous example and few-shot learning, and they can be more valuable. As a concrete example, look at this scenario. So let's say that you're asking, you want to glean this information, capital of France is Paris. But then let's say this is an intermediary step. You want to feedback the answer to some API service that requires a specific format to upload that result, maybe in a JSON dictionary key or whatnot. So you can get that by providing it with a few examples of how you want the format to be. So make it like a dictionary or something. So so one advantage is, zero shot is simpler, lower token count. It allows larger window for context. This is becoming more and more irrelevant because newer LLMs have very large context size. But at the beginning, like there's a limit of the amount of input size that you can prompt the language models with. With the few shot, it's better alignment to your responses and better accuracy to complex questions. So why prompt engineering? So prompt engineering, remember that these are gradient-free updates, right? We're not training the model. We're not, on one side of the spectrum, you have full parameter fine-tuning. You're training a language model with lots of data, and you're doing gradient descents and whatnot, right? But with prompt engineering, you have a pre-trained model, and you're just using different prompting techniques to extract better utility to whatever your definition of utility is. And it's minimal, simple input, and you can do online inference time updates to your answers, okay? And in the middle, see, this requires more of a course, but they're like this parameter efficient fine-tuning strategies like, factorization, et cetera, which allows you to train models in a more parameter efficient way, which is a lecture on its own. So usually I just wanted to leave you with the basics of prompting. So usually the way you do it is you have certain roles. System role actually gives overall core instruction, and then you can have more granular instruction. So here's an example of, let's say I'm prompting GPT-4, and with like I'm asking it to predict what's the stock price is going to be tomorrow, because that's all we need to know, right? Like that's everyone's first question. So you're a stock market analyst, and then you know that's you define the system, and then the assistant is basically the core, like the subtask that you're asking, and then the user could be a human or it could be another AI. Okay. And usually you send this as a discourse, like structured messages. And typical LLM hyperparameters include like top P, which is basically what percentage of the tokens in the probability distribution you wanted to use. And then there's some repetition penalty. Temperature is the randomness of choosing a token, and maximum sequence length is important. It defines the size of the input context window, which usually depends on the LLM. Prompting techniques, I mean, as I said, that it's an active research area. Like, you know, a lot of things can affect. One example is like stylization. So if you ask, instead of like, you know, solve this problem, solve beam search, you can ask it, right, I'm a CS student using LLM for cheating. How do I write beam search? It could give you a better answer. Who knows? So an explicit step-by-step instruction. One important technique is Scott's chain of thought that out of all the many different techniques, this was one of the, a little bit different, like one of the key techniques changed towards decomposing answers using intermediate reasoning. So the idea is that you can ask it, especially this is effective for mathematical reasoning kind of things. So if you have a standard prompting, if you ask a mathematical question, it will give wrong answer. But if you decompose that into intermediate steps, it usually gives the right answer. And it showed that, you know, just by changing this prompting template, you can achieve a far better answer. In fact, it was shown that if you just include the word sentence significantly, so just simply adding a phrase saying, think through this step by step, improves the answer for some for large language models. Okay, yeah. So. And so evaluation of benchmarks, so how do we evaluate this? So before we have seen superglue and glue benchmarks, but now it has evolved with the evolution of LLMs. We need newer benchmarks, newer, harder tasks. And here are some benchmarks with different tasks, and it's sort of like dynamic in nature, like Big Bench and MMLU. These are dynamic in the sense that it's rolling submission. So someone comes up with a new task, new data set, they would incorporate this into the benchmark. And these are harder data sets, and there's still a lot of tasks like human creative problem solving that language models are not really good with. But anyway, so this is, let's stop over here, and yeah, good luck with the assignment, and thank you.